Hello everyone, let's solve this LeetCode problem 102, binary tree level order traversal. Let's read this problem. Given the root of a binary tree, return the level order traversal of its nodes value from left to right, level by level. So here is the example. Give this example. After we level order traversal, so we got the result here. So 3 is one level, 9, 20 from left to right is another level, 15, 7, and this is the third level. This is the problem. So in the previous video, I actually solved this problem using BFS, but in this video, I'm going to solve this problem using DFS. Okay. So let's go with this example. Here is the input 3, 9, 20, 9, 9, 15, 7. The same as this example here. So first, let's check the root. Root is 3, right? So the deep from the root here, the deep, we have 3 here. So the deep is 1. So the result size is that this one is the result, right? So at the beginning, the result size here, is 0. Result size is 0. And then what we do, we just actually, we just push this, so kind of, we new array, because here we will check the result size if smaller than the result size smaller than the depth, and then we will new and a result array here. We will do this way. Okay, this is basically what we do here. Okay, so the for the DFS, the stop condition is gonna be if root equals to none, and then we will return. Okay, this is our basic return, the stop condition of the binary, the DFS. Okay, so and then what we do, we put a 3 here, we add a 3 here, and then we will check and then we will do DFS for the left child and right child. This is basically the DFS. And then after that, what we do, we check the none. So we check the none, the depth is 2 now, because we have 1, 2, right? So the result size here is 1, right? So result size is 1. And then we check the result size and smaller than the depth, yes. And then what we do, we new another one in the result. Okay, so what we do here, we new this one. And then we will check, and then we will get the none. We put none here. We put a none here, and then we will check the none have a left or right child here. So the left child of none will do DFS. The right child here also do DFS. In this case, because it's already none don't have left or right child, so we just return. We return to 3, and then we do the right child of 3. So next element is gonna be 20, and then the depth here also is 2. So the result size here is 3, and then is 0, 1, so it's 2, right? So basically here is 2. So when here is 2, what we do, so we don't have to new a new one, so we just directly put the 20 in the. Okay, so we just do depth minus 1 depth is 2 minus 1 is 1, so 0, 1. So we just put here 20. Okay, and then we will check the 15. The depth for the 15 is 3. And then the result size here is 0, 1 is 2, right? So it's 2. And the 2 is smaller than the depth. And then what we do here, we will new list. We will new a new list, and then we will put a 15 over there. Okay, we will put a 15 here. And then the next step, and then we return to here, and then we go for the 7. So once we do 7, the depth here is 3. The size here is 1, 2, 3. So it's 3. So we don't have to new a new one. So what we do, we just add this in the result. So we'll be get the index of 3 minus 1 is 2. So 0, 1, 2. So we will do it. We will add it here. This is 7. And then we return, and then we just simply return the result. This is definitely this kind of the algorithm. I will give you another example. Maybe it's more easier to explain this problem. Okay, it's here. Okay, for this one, actually is 3, 9, 20. 15 actually is here, and 9, 9, 7. Okay, this is basically the tree. So for this problem, the root is 3, the depth here is 1. And the size, result size here is 0, smaller than the depth. So what we do, we new an array list here, and then we put a 3 here. And then we do the DFS for the left child again. So the left child is gonna be none in this case. It's gonna be none. The depth is 2. The result size here is only 1, so here is 1. That means we are going to new one more array in the. Okay, so that means we are doing this, and then we put none here. We put none here. Okay, this basically we're doing, and then what we do here, we have this one 15. So and then we will do 15. So the depth here is gonna be 3. And the result size here is 2, is smaller than that. So what we do, because it's smaller, so we knew another one is gonna be like this. And then we put a 15 here. We put a 15 here. Okay. And then we have none. We have none here. We return to here. We do this. This one is none. We don't do anything. And then we return to here. And then we do the this child. And this child is none. Here is none. And then we return to 20. And then we do the right 7. Yes, so kind of we start from a 3, and then we go none, and the left child of none have 15, and then we return to here. We do the right child. Right child here is none, and then we return, and then we do 20. Next step, we are going to do 20. So the depth for 20 is 2. The result size now is 3 greater than the depth, so we don't have to new a new array. So what we do here, we just do this. We add 20 in the instead the array is get the depth minus 1 is 2 minus 1 is index is gonna be 1, so 0, 1. So we will add it here 20. 20. Okay, and then the next step after we do this, the left child of 20 is 0 and the right child of 20 is a 7. So what we do next step, we are going to do 7, and then the depth here is 3, and the size here the 3 is equal, so we just added the 7 to the depth minus 1. That's the index. Depth here is 3 minus 1 is 2, so 0 1 2. So it's here, we just added here. So basically this is the tree we are trying to get it this way. Okay, so talking about the time complexity for this problem, it's gonna be ON because we just did traversal once. And the space complexity for this problem, is OH, is the depth of the tree. Okay, let's start coding. So for this problem, let's start coding. Let's do this way. Okay, so first we're gonna do a list. Okay, we will store our result in this list of list integer. And this declare our return result. So, and then what we do here, oh, sorry about that. So this one, the result, what we do, we actually make it outside of this function. Okay. Okay, and then we do DFS. DFS, later we will put that one. So we return result. Okay, and then we will write in the function of DFS. The function of DFS is gonna be void DFS. Okay, we are going to put a tree node root here and depth here. And what we do here, we check if the root equals to none. If it equals to none, what we do, we just return. Okay, this is the DFS. This is the stop, the basic condition to stop our DFS. And then what we do, we check if the result size smaller than the depth. Smaller than the depth. If it's smaller than the depth, what we do here, so we will check if the, oh, sorry about that. If this one's smaller than that, what we do, we just do this. Result dot get dot depth minus 1. Okay, dot add root dot value. Okay, after we do this, root the left depth plus 1. DFS root the right depth plus 1. Okay, so basically the code here, we can see, let's run the code first to see if it works. Okay, here. Oh, here we put a root and a 1. Okay, let's run the code. Okay, it's accepted. So basically the code we can see is first we declare our return to the result. Okay, it's a list of list. We put this, we declare this one outside for our method. Okay, so this is DFS. The DFS, we start from the root 3, from the root, and the depth of this level is 1. Okay, so, and then we return. So this is the depth, the method, the DFS method. So the input of the method is root and the depth. Okay, and then this is a condition to stop. It's a root. When root equals to none, we will return. Okay. And here is the things like when the result of size, if smaller than the depth, that means that's a new level, right? So we add here, add a new array list here. I just showed you guys when we're doing that. Whenever the result size here is 1 smaller than the depth 2, and then we new a list array here, and then we add the none to here. Okay, so that's a new level. And then see how we add the root. The value here is depth minus 1. That's the index. The depth is 2 minus 1 is 1, right? 0, 1, right? So it's similarly here is 3 minus 1 is 2. So 0, 1, 2. Yeah. This is basically how they get the index of the value we are trying to put here. So, and then we do the root the left DFS, root the right DFS, and then our depth plus 1 because we have one more level. So beginning is 1, and this is 2, and here is a 3, right? So we update our depth plus 1. So basically, this is a algorithm, and then we need to talk about the time complexity between BFS and the DFS. So so which algorithm we should choose if we do the binary tree level order traversal? Here has some situation. So the DFS, the space complexity is ON, right? So the BFS is O 2 to the power of H minus 1. So if our binary tree is a complete binary tree, I mean, like they all have the kind of the all the child, all the left and right child, they do have the child. Okay, so if in that way, we will use DFS because the OH is gonna be smaller than the Y, the OW. Okay, this part we can call it OW. The maximum of the nodes for that level. Okay, so if the tree is a long depth tree, like only have a right child. For example, we have 3 here, we have a 20, we have 7, we have 15, we have 9, we have 4, we have 2. You know, if we only have one child, it's a long depth tree. But in the left side we don't have that much child. So in this case, the space complexity gonna be O1. We as ON. That means the BFS gonna be O1. And if we use DFS, it's gonna be OH. OH is too long, right? So in this way, we are using the BFS. Okay, so it depends. Okay, let's submit the code. Let's check. Okay, our algorithm is faster than 100% of the Java Online submission. It's very good. Okay, thank you for watching. I will see you next time.